How can a diesel engine move a 40-ton truck using air? The question seems absurd at first. However, the answer explains why modern trucks can climb mountain passes, maintain highway speed, and haul gigantic loads without apparent effort. That answer begins inside the turbo. Every time the driver accelerates and the engine demands more power, the exhaust gases stop being waste and become a force capable of multiplying the engine's performance. That is why the turbo becomes one of the most decisive components of a heavy truck. Without it, even a large displacement engine would be slow and limited by the amount of air it can draw in on its own. And it all comes down to a fundamental idea: a diesel engine generates power according to the air that enters the combustion chamber. The more air it receives, the more fuel it can burn, and the more energy it can deliver. But there is a physical limit to what a naturally aspirated engine can draw in. That is where the turbo appears, a solution that reuses the energy of the exhaust gases and transforms it into compressed air, ready for the next combustion cycle. In a heavy truck, this component works under extreme conditions. Every acceleration, every prolonged climb, and every stretch of highway subjects the turbo to extremely high temperatures, millimeter-controlled pressures, and rotational speeds that exceed the capabilities of any conventional mechanical component. The turbo transforms the force of the exhaust into real power, and it does so continuously, steadily, and efficiently. That is why the key question arises: what exactly is this component? And how does it manage to harness the exhaust gases to multiply power? Inside the turbo, everything happens around a common shaft that connects two key elements. On one side, a turbine driven by the exhaust gases. On the other, a compressor responsible for sending compressed air to the engine. That direct connection makes it possible to transform energy that would normally be lost into a constant source of boost. From that shaft begins the true movement. The turbine is located on the exhaust side and receives the impact of the hot gases expelled at high speed after combustion, causing it to spin. That movement is immediately transmitted to the shaft, which in turn drives the compressor located on the intake side. The compressor draws in ambient air, compresses it, and sends it to the engine's intake manifold. Thanks to that boost, more air enters per cycle, which allows more fuel to be injected and more power to be generated without increasing displacement. But why does a heavy truck need a turbo so urgently? The reason is simple. A large diesel engine moves a huge volume, yet it still needs more air than it could naturally draw in. Without a turbo, the time it would take for a naturally aspirated engine to fill its cylinders with fresh air would be incompatible with the power demand required to move a 40-ton vehicle. Acceleration would be poor, consumption would skyrocket, and the ability to maintain speed on inclines would be extremely limited, which is why forced induction is not a luxury, but the starting point for a modern truck to have the performance its daily work demands. Moreover, a turbo for a truck is very different from the one used in a conventional car. Turbos in light engines are designed to offer quick response, favor dynamic driving, and deliver power across variable load ranges. A heavy truck, on the other hand, requires stability, thermal resistance, and durability. Its turbo must withstand higher temperatures, sustained pressures over long periods, and an almost continuous operating regime. The size of the turbine is larger, the materials are more robust, and thermal management becomes much more critical. The priority is not instant response, but maintaining constant full load operation over miles without failure. To achieve that constant stability, the entire operation of the turbo revolves around the balance between flow and efficiency. The more air that enters the engine, the more fuel can be burned and the more energy is released, which is why the turbo increases air density and improves combustion while reducing emissions. From that principle onward, the evolution toward more advanced turbos has allowed diesel engines to comply with increasingly demanding regulations without sacrificing power, turning an engine apparently limited by its size into a machine capable of generating enormous levels of performance. However, working with high pressures and extreme temperatures comes at a cost. The turbine can face more than 800 degrees, while the compressor spins at speeds that easily exceed 100,000 revolutions per minute. And in the midst of that constant strain, the internal shaft can only remain stable thanks to a millimeter-precise lubrication system. Each component is designed to withstand continuous stress, extreme limits that make understanding the operation of the turbo in depth even more fascinating. It sounds simple, a turbine that drives a compressor. But how are those enormous pressures really generated, and what happens to the exhaust gases inside the turbo? Inside the system, everything begins with the energy carried by the gases as they leave the engine. Intense heat, speed, and expansion combine in a single flow that strikes the turbine with constant force. What in a naturally aspirated engine would be lost through the exhaust is here transformed into movement capable of compressing fresh air into the engine. That energy does not arrive in a single form. The exhaust gases combine extreme heat and speed in the same flow. In a heavy truck, temperatures in the turbine area can range between 500 degrees and more than 800 degrees during a prolonged climb or a stretch of constant load, while the gas velocity increases as the engine works under greater demand. The greater the engine load, the faster those gases circulate, and the greater the energy available to drive the turbine. When that flow enters the turbine, a very precise physical process begins. The gases pass through the volute, a snail-shaped cavity designed to accelerate their path toward the blades. As they move forward, the internal geometry guides and directs them until they impact with controlled force, and at that point, energy transfer occurs. The pressure and speed of the gas are converted into rotational movement of the turbo shaft. After delivering its energy, the gas expands and exits toward the exhaust, now cooler and with lower pressure. That rotation does not stop at the turbine, it continues through the shaft that connects both ends of the system. On the intake side, the compressor draws in fresh air from outside and compresses it through the rotation of its blades. Compression increases air density, which allows a greater mass of oxygen to enter in each engine cycle, and turns that increase in density into the foundation of the turbo's performance, since more oxygen implies more complete combustion, more energy released, and therefore more power available to move the truck. However, this process is not perfect, and there are losses due to friction in the shaft bearings, turbulence inside the volute, and limitations caused by the extreme exhaust temperature. In addition, the turbo must be manufactured with materials capable of withstanding thermal expansion, abrupt temperature changes, and continuous stress over hundreds of thousands of kilometers. The efficiency of the system depends on every detail, from the shape of the blades to the quality of the lubricant and the precision of the assembly. And that same constant pursuit of efficiency also explains why the turbo does not always operate at its optimal point. Not every engine speed generates the same exhaust velocity, nor does every compressor respond the same at different pressure levels. That is why compressor maps exist to show the efficiency zones of the system. Operating outside those ranges can generate excessive heat, performance losses, or even the risk of mechanical overload. Here, an obvious problem arises. If the exhaust gases drive the turbine with such force and that energy can constantly vary, what prevents the turbo from generating more pressure than the engine can withstand? The turbo does not always work at its limit and needs to maintain a constant balance between power and control. Although the energy from the exhaust is enormous, the engine can only admit a certain pressure before dangerous temperatures, excessive mechanical stress, or serious failures appear. That is why regulation systems become essential to keep operation within a safe margin. To achieve that control, the first key element comes into play, the wastegate valve, whose purpose is to divert part of the exhaust gases before they reach the turbine once the desired pressure has been achieved, thus preventing the turbine from continuing to accelerate and the compressor from generating more pressure than necessary. The wastegate can be internal, integrated into the turbo housing itself, or external, mounted as a separate component. In truck engines, electronic control is common, adjusting the valve opening according to engine demand, load, and thermal conditions. When intake pressure reaches the target value, the control unit orders the wastegate to open, and the excess gases are diverted directly to the exhaust, reducing the energy that drives the turbine. The second control device is the relief valve, used to protect the compressor side from sudden pressure spikes. Unlike the wastegate, which acts on the exhaust gases, the relief valve operates on the intake side. Its function is to release pressure when a sudden increase occurs that could compromise the integrity of the compressor or the boost piping. This component is especially useful in two-stage configurations or in engines that operate under highly variable loads, where the turbo can change speed rapidly. It is an additional safety system that stabilizes pressure and prevents surges that could damage the compressor wheel. However, the most important advancement in pressure management for heavy engines is the variable geometry turbo, known as VGT. Instead of having a fixed entry for the exhaust gases, the turbine is surrounded by movable vanes that modify the flow according to the engine's needs. When the vanes close, the gas velocity increases, the turbine spins faster and the engine receives more pressure. When they open, the flow is reduced, slowing the turbo. This system offers extremely precise control and makes it possible to maintain stable pressure even when the engine changes load or speed. The VGT provides significant benefits. It reduces the response delay typical of large turbos, improves efficiency at low revolutions, and prevents excessive pressures when the engine works at its limit. In addition, in many trucks, the VGT is integrated with the engine brake, modifying the position of the vanes to generate back pressure in the exhaust and help reduce speed without using the service brakes. This versatility makes the VGT practically the standard in modern heavy engines. These three systems work together to maintain balance. The wastegate regulates the overall amount of energy entering the turbo, the relief valve prevents dangerous spikes in the compressor, and the VGT precisely adjusts the response in real time. Without this combination, pressure would be erratic, unpredictable, and potentially damaging to the engine. But pressure control does not solve a fundamental problem. When the turbo compresses air, it also raises its temperature, and that heat reduces the density of the flow, limits the available power, and increases the engine's thermal stress. If compression generates so much heat, how does the truck manage to maintain performance without that temperature increase, ruining the system's efficiency? Within the intake circuit, a key component then appears that completely changes the behavior of the compressed air. Before reaching the cylinders, the flow passes through an intercooler that reduces its temperature and restores density. When the turbo compresses air, the thermal increase is inevitable, and without this intermediate step, the air would arrive less dense, with less oxygen per volume, and with a direct impact on combustion and the real power available. In a heavy diesel engine, this problem is amplified. The engine operates for long periods under constant loads, generating high temperatures in a sustained manner. The turbo sends air at high pressures, and the temperature of the compressed air can easily exceed 150 degrees. Without a system that cools that air before it reaches the cylinders, efficiency would collapse and engine reliability would be compromised. The intercooler is therefore an indispensable element, not a mere accessory. To fulfill that function, the intercooler acts as a specialized radiator located between the compressor and the intake manifold. Its mission is to reduce the temperature of the pressurized air in order to increase its density and allow the engine to burn more fuel in a controlled manner, thus generating more energy in each cycle. That thermal difference can be notable. In many heavy trucks, the air arrives from the turbo extremely hot and leaves the intercooler at a temperature very close to ambient, even under high load. According to the type of system used, there are two main intercooler configurations, air-to-air and air-to-water. The air-to-air system is the most common in highway trucks, since it takes advantage of the external airflow itself, driven by the vehicle's speed or by the fans, to cool the radiator fins and dissipate the heat from the compressed air circulating inside. This solution stands out for its robustness, efficiency, and low maintenance requirements, while the air-to-water intercooler appears as a more compact alternative that allows more stable thermal control at the cost of incorporating an additional cooling circuit. Due to its simplicity and reliability, air-to-air remains the predominant option in heavy vehicles. The process inside the intercooler occurs in several stages. First, the compressor sends hot, pressurized air toward the radiator. That air enters a series of internal ducts surrounded by thin metal fins designed to maximize the surface area for heat exchange. Meanwhile, external air passes through the intercooler from the front of the truck. The heat from the compressed air is transferred to those fins and dissipated outward. As a result, the air leaving the intercooler is significantly cooler and therefore denser. That drop in temperature has a direct impact on engine performance. Cooling the air can increase its density by more than 30%. This means more oxygen available, more efficient combustion, and greater power delivered by the engine without the need to increase turbo pressure. In addition, cooler air produces more stable combustion, reducing emissions and extending the service life of the engine's internal components. The intercooler also contributes to the overall durability of the system, since cooler air reduces combustion temperature and decreases the thermal load on pistons, valves, and the cylinder head. Furthermore, it stabilizes the turbo's working environment, since an engine that combusts in a more controlled manner places less stress on components subjected to high temperatures. Even so, even with an efficient intercooler, a truck subjected to long working days can generate extreme temperatures for hours. The turbo must withstand that continuous heat, along with rotational speeds that challenge any traditional mechanical component. But what happens inside the turbo itself when it works for hours under high temperatures and rotations impossible to see with the naked eye? Under those extreme conditions, the shaft and its bearings remain spinning without rest, supported only by a constant film of lubrication that prevents direct contact between the parts. At more than 100,000 revolutions per minute and surrounded by continuous heat, this small internal assembly maintains the system's balance, and its precision determines not only the life of the turbo, but also a crucial part of the engine's performance. At the center of all that movement appears the shaft, the true backbone of the turbo. It connects the turbine, driven by the exhaust gases, with the compressor that sends pressurized air to the engine. Its function is to transmit rotation without flexing, vibrations, or losses. It works in an extremely hostile environment, one side exposed to the heat of the exhaust, the other to the relatively cooler air of the compressor, all while spinning at speeds that do not allow the slightest imbalance. If the shaft suffers deformation, no matter how minimal, the turbo stops functioning properly in a matter of milliseconds. To withstand those conditions, truck turbos primarily use hydrodynamic bearings, a system in which the shaft does not rest directly on metal, but instead floats on a thin film of pressurized oil. That film, microns thick, is responsible for keeping the shaft centered, reducing friction and dissipating part of the heat generated by rotation, becoming the key element that allows the turbo to continue operating under extreme loads. The correct operation of the turbo depends entirely on that oil film. The pressure must be maintained within a very precise range. If it is too low, the shaft loses its cushion and comes into direct contact with the bearing walls, generating instant friction. If it is too high, it can cause sealing problems and affect the internal balance of the system. The oil not only lubricates, it also cools, stabilizes the shaft, and prevents deformation due to heat. Under those same thermal conditions, one of the most common risks in turbos appears: oil carbonization, a phenomenon known as coking. When oil remains exposed to extreme heat for too long, especially after long full-load cycles, it can break down and form hard deposits in the lubrication passages. These residues reduce the flow of oil to the shaft and bearings, creating a vicious cycle where lubrication decreases, friction increases, heat intensifies, and carbonization accelerates. If not controlled, the turbo can begin to degrade from the inside, without the driver noticing immediate symptoms. The most critical scenario occurs when lubrication fails even for a single second. At that instant, the shaft stops floating on the oil film and rubs directly against the metal. Friction multiplies, temperature rises suddenly, and the bearings can deform or break. The shaft loses its alignment, the blades can rub against the housing, and the turbo is destroyed almost instantly. In fact, many serious turbo failures originate in extremely brief episodes of lack of lubrication. To prevent this type of failure, modern engines incorporate several protection mechanisms: sensors that monitor oil pressure and temperature, dedicated lubrication lines to the turbo, calibrated restrictors to guarantee the correct flow, and return systems designed to prevent accumulations that could impair circulation. The engine's electronic control can also reduce turbo load if it detects abnormal lubrication or temperature conditions. Despite all these measures, the turbo remains a delicate component working under extreme conditions. And when something begins to fail, whether due to insufficient lubrication, foreign object ingestion, or thermal overload, degradation can be rapid, noisy, and costly. With such a delicate system working at such high speed, what really happens when a turbo begins to fail, and why can some failures destroy it completely in seconds? The moment that balance is broken, the entire assembly begins to react immediately. The turbine, the compressor, the shaft, and the bearings depend on one another, and a single parameter out of range is enough to trigger a chain reaction that the engine cannot compensate for. The most common cause of failure in a truck turbo is lack of lubrication. If oil pressure drops, or if the flow becomes obstructed, the shaft stops floating on the lubricating film and comes into direct contact with the bearings. That contact generates instant heat, deformation, and loss of alignment, and from that point on, the integrity of the turbo is compromised in a matter of seconds. Within that same scenario appears another common threat: oil carbonization, known as coking, where hardened deposits clog the lubrication passages and reduce oil flow to dangerous levels, especially in engines subjected to many hours of high load. Another source of failure is the ingestion of foreign objects: small particles from a damaged air filter, metallic fragments, or even debris drawn in under extreme conditions that can strike the compressor wheel. At the speeds at which a turbo spins, a tiny fragment is enough to unbalance the rotor, bend a blade, or cause irrecoverable vibrations, and on the turbine side, objects carried by the exhaust can wear down or fracture the blades just as quickly. Sustained thermal overload is another natural enemy of the turbo. A truck that works long hours climbing slopes, hauling heavy loads, or subjected to intense acceleration cycles generates very high temperatures in the turbine. If cooling and lubrication are not sufficient, the materials expand more than expected, the bearings lose tolerances, and the shaft can deform due to heat. All of this affects the balance of the assembly and accelerates internal wear. The symptoms that a turbo is failing are usually clear. A sharp whistling sound that did not exist before may indicate a leak or an imbalance. A sudden loss of power reveals that the compressor is not generating the expected pressure. Exhaust smoke is also an indicator. Blue smoke signals that the turbo is allowing oil to pass into the intake. Black smoke indicates poor combustion due to lack of air. Metallic noises coming from the turbo are critical signs. They mean that the compressor or the turbine are rubbing against the housing, a prelude to imminent failure. Speaking of a turbo exploding may seem exaggerated, but the term intuitively describes what happens when the system is destroyed suddenly. A turbo does not explode like a device, but it can suffer a violent internal rupture. If the shaft breaks or bends, the blades can strike the housing with enormous force. Rotation at tens of thousands of revolutions per minute turns any loose fragment into an internal projectile. The housing usually contains these fragments, but the destruction of the turbo is total. In the worst cases, some of the debris can enter the intake and reach the engine, causing serious and costly damage. Truck turbos endure more than car turbos for several reasons. Their rotating mass is greater, the temperatures they withstand are higher, the work cycles last hours instead of minutes, and the oils are subjected to continuous stress. Despite this, modern turbos have self-protection systems. Electronic control can limit pressure if it detects abnormal parameters, the VGT can modify geometry to reduce load, and sensors monitor oil pressure and temperature. In a turbo that spins at extreme speeds, the margin between functioning perfectly and failing destructively is surprisingly small. And understanding these symptoms makes it possible to appreciate the value of each component in the system. After seeing how a turbo can go from operating with absolute precision to failing in a matter of seconds, it becomes clearer to understand the real complexity of this system. What at first glance appears to be a metal housing attached to the exhaust is, in reality, one of the most demanding and sophisticated assemblies working inside a heavy truck. And everything we have analyzed, from the energy of the gases to the fragility of the bearings, is part of the same mechanism designed to transform heat and pressure into useful force. The turbo is, in essence, a device that harnesses wasted energy. It converts the heat and speed of the exhaust into a flow of compressed air that feeds the engine with greater density. That idea, seemingly simple, requires a precise infrastructure. A turbine capable of withstanding extreme temperatures, a compressor optimized to generate stable pressure, and a shaft that transmits movement at speeds impossible for virtually any other mechanical component of the engine. To this process is added pressure control, which keeps the turbo within its safe operating range even when the engine changes load or speed. The wastegate, the relief valve, and the variable geometry work together so that pressure never exceeds the engine's limits. At the same time, the intercooler reduces the temperature of the compressed air, ensuring that it reaches the cylinders cool and dense. It is a thermal, mechanical, and dynamic balance that is maintained hundreds of times per minute as the truck moves forward. And at the center of it all lies the most delicate component, the shaft and its bearings. A film of oil only microns thick keeps the system suspended and stable. If that lubrication fails, even for an instant, the turbo can go from functioning perfectly to being completely destroyed. That is why understanding its failures is not sensationalism. It is recognizing the extent to which this system demands precision to operate with the regularity required by a truck engine. In the end, what this journey shows is that the turbo is not an accessory nor an optional addition. It is the component that allows a heavy truck to move dozens of tons, maintain speed on demanding roads, and deliver efficient performance without skyrocketing fuel consumption. It is a work of engineering that combines thermodynamics, advanced materials, precision mechanics, and electronic control. Its reliability is the result of decades of evolution and refinement. If you want to continue discovering how the machines that move the world work and understand the engineering behind each one, you can subscribe so you do not miss the upcoming videos. There are still many equally fascinating systems that deserve to be analyzed at this level of depth. Thank you for joining us.